Good afternoon, everyone. My name is Bruni. Now I'm a PhD candidate in the Polytechnico di Milano in Italy. Today, my presentation consists of 5 parts. In the first part, I will introduce my reflection about the difficulties and problems of studies for whale polygonization. The whale polygonization has been studied over 30 years. The effects of it are relatively clear, but the mechanism are still unknown. You can find some research showing that the mechanism of whale polygonization is concerned with binding resonance for whale set, real ping-ping resonance, and there are some other possible reasons. But by far, there's no consensus. From my viewpoint, one of the difficulties to study this problem is that it is not easy to simulate the polygonal wear process. But once we achieved this, we can figure out each step from initial out-of-round profile to the final worn, possibly high-order profile. And so this is a very important tool to review the mechanism of whale polygonization. Another problem I want to mention here is about resonance speed. Usually, generic logic to study whale polygonization is to find a resonance frequency from vehicle system or from track system that is equal to the outside excitation frequency caused by polygonal wear at a specific frequency. But the problem is, which speed should we use, the maximum speed or the average speed? This problem could be more difficult to answer if you study the metro vehicle, because metro vehicle will change the speed for more than half of the running time. And in my research, we give some ideas to these problems. Now let's come to the second part, simulation method for polygonal wear. Here you can find a schematic flowchart of this method. Firstly, an initial polygonal wear profile is put into a short-term dynamic model, and then some wheel-real contact parameters like normal force, the wheel-real contact positions will be obtained, and this data will be used to calculate the wear depth for each contact patch by using some wear models. And after that, the wear depth around the wheel circumference is accumulated and filtered. And based on this, we can get a new circumferential wear profile, and this profile will be sent back into the short-term dynamic model. And after iteration, we can finally get the development process of the polygonal wear. And here I present some details problem inside of this simulation method. The wear model I use is based on the wear friction power, which assume that the excavated, the removal material is proportional to the wear friction power. There is a new challenging work when you simulate the polygonal wear. The wheel profile, the wheel circumference profile is a closed line compared with the wheel trend. I mean, the point at 1 degree and the point at the 360 degree, they are connected to each other. So some conventional curve fitting methods cannot be used because it cannot make sure that the connecting point is continuous and differentiable. And simulation results show that even a small distance, the small disturbance at the connecting points will bring about a huge impact. So in order to solve this problem, we propose to use Fourier series expansion function to fit and to smooth the curves. And you can find more detailed explanation from my paper. Here I present examples about the wear development of an elliptic whale, the second order of whale, in the different coordinations. You can observe the increasement of polygon depth and also the changes of polygon order. But this is not the end of the study for the simulation method because I find there are some other factors that can significantly affect the simulation results, and I only select one to present, and that is the whale profile updating condition. The third D here is the maximum distance between the adjacent whale curve. Theoretically, the third D should be selected as small as possible because a simulation with a too large third D is quite different from the real whale process. If a too small third D means a large number of iteration. In this case, some small simulation error, for example, an error coming from the curve fitting method in the upper stage will be accumulated, will be magnified if a large number of iteration is applied. So too small third D should also be avoided. You can find more descriptions about these studies in my paper. And now let's come to an interesting part, a case study for a metro vehicle. This metro vehicle is featured with linear motor traction technology. An initial fourth-order polygonal whale was found after whale reprofiling, and it grows into 8th and 9th order polygonal whale. We were told by the staff of the metro company that the ride comfort of this metro vehicle is not so good. So at first, we did simulation to calculate the ride indexes at different speed level with 8th and 9th order polygonal whale. And we found that when the vehicle speed is at around 40 kilometers per hour, the ride indexes become extremely severe. And after analysis, we realized this probably because when the vehicle is close to the 40 kilometers per hour, the outside excitation frequency caused by polygonal whale is around 40 hertz, which is quite close to the natural frequency of the bouncing motion of linear motor. So in this case, the resonance of linear motor will be triggered, and the vibration of linear motor will be transferred to the car body, which result in the bad rad index. And after that, we did some long-term on-track test at 1 month, 2 months, and 6 months after whale reprofiling. Here I present some typical measured data on a straight track zone between the two stations. The continuous lines are time history of speed, and because this vehicle runs in ATO mode, so for each time the speed line is the same, and the stepped line here is the ride indexes. You can easily find some features that a few months after whale reprofiling, the vertical rad indexes become worse, and especially at the speed around 40 kilometers per hour. So this result is consistent with our previous simulation result. And for the lateral rad indexes, you can see that after whale reprofiling, the lateral rad indexes is worse, but it improves in the following months. This is very strange phenomenon. But in general, we can see that the dynamic performance of vehicle has different features in different stages. We also realized that with initial fourth order, the vehicle will produce 40 hertz at around 85 kilometers per hour. So in this case, it can trigger the resonance of linear motor. And we also got the distribution of the speed level according to the measured velocity data, and you can see, and you can see that the most frequent speed level is at around 85 kilometers per hour. So the polygonal whale at 85 kilometers per hour with an initial fourth order will be very important. And we did the simulation in this case. And here you can find the simulation result. I divided this process into two phases. In the first phase, you can see that the initial fourth order quickly divided into eighth polygonal order. And in the second phase, the order does not change apparently, but the depths start increasing. We also did simulation in some other speed. Here you can find the wear at the 30 kilometers per hour. You can find the shape is quite different, and more importantly, the wear speed is relatively extremely smaller than the wear at 85 kilometers per hour. So based on this study, we propose an explanation for the wear polygonization of this metro vehicle. In the first phase, with initial fourth order polygonal irregularity, the wheel will produce 40 Hz excitation, and it will trigger the resonance of leader motor. The vibration of the leader motor transferred to the carburetor and also to the wheel set. In this stage, the polygonal wear develops from initial fourth order into eighth and ninth order. And in phase 2, when eighth and ninth order polygonal wear has been formed, the high order polygonal wear will no longer, at 85 kilometers per hour, will no longer lead to resonance of linear motor. But when the vehicle velocity comes to the 40 kilometers per hour, the resonance will happen again in a very short time. In this stage, the depth of high order polygonal keeps increasing at a relatively low speed. And based on this case study, we propose some new understanding, some new ideas for the development of wheel polygonization. Firstly, the development process of the wheel polygonization could be divided into different stages, and the wheel profiles and the vehicle dynamic behaviors have different features in different stages. Secondly, the investigation for the mechanism of wheel polygonization could start with initial low order instead of high order. If you do this, you can find the corresponding resonance frequency you are looking for will be reduced to a relatively low frequency. And thirdly, we find that identifying a specific resonance speed will lead us a specific frequency rather than the speed frequency range. Now let's come to the conclusion. Let's review what we did in this research. Firstly, we established a long-term iterative wheel model, and we studied some important parameter sightings to try to improve the accuracy of simulation. And the second point, we try to analyze wheel polygonization of a metro vehicle. Thirdly, we find the development of polygonal wear can be divided into different phases. And finally, we realized that identifying a resonance speed is an important point to study the formation mechanism of wheel polygonization. Okay, thank you, everyone. Thank you.
Thank you.